In this second video, we will start looking at the co-integration representations. If you have a look at academic papers about co-integration, you will find that there is no uniform way to represent the co-integration relations. So you better get used to seeing different representations. There are, however, three often used ways to represent the co-integration relations, and we will have a look at these three representations today. After having seen these representations, you should be able to reconstruct them yourself. So let us start with the first, the Phillips triangular representation. Recall that the rows of A prime contain the co-integrating vectors. Now, these co-integrating vectors are not unique, but they do form a basis for the co-integration space. Now, to make this a bit more concrete, as an analogy, think of the two-dimensional space, where the unit vectors 1, 0 and 0, 1 form a basis for the entire space, since you can express every point as a linear combination of these basis vectors. But they are, of course, not unique. Also, the vectors 2, 0 and 0, 2, for instance, span the entire space. Okay, so back to my A prime matrix. I start from these co-integrating vectors in the rows of A prime. I will also normalize this first element to unity, which I can do without loss of generality. If needed, you can always reorder your series such that this first element is equal to 1. Now let us have a look at the remaining rows, which are the remaining co-integrating vectors. And I will re-express them in such a way that I obtain a 0 element in the first column for each of them, as you can see already here. I can do that by subtracting the corresponding element in the first column from each row. The new co-integrating vectors will still be linearly independent from the others, and they also span the co-integration space still. Now, the steps that are involved here are in detail explained in Hamilton, so have a closer look at that derivation. Derivation itself is not so interesting. That's why I also go over it more quickly. But what is more important to understand is that I aim to re-express these co-integrating vectors in such a way that I break up A prime in two parts. In the first part of dimension h times h, I retrieve the identity matrix. And in the second part, I have a gamma matrix, which is of dimension h times n minus h, since I need to have n columns in total. Now, why is this equivalent formulation of A prime so important? Well, first of all, it allows us to answer the question why we can't have n co-integration relations. Why? Well, if we would have n co-integration relations, in the notation from the previous slide, h would then be equal to n. But that also means that I would have the identity matrix of dimension n here, and the second part would not be there anymore. Now, why is this not possible? Well, what would our co-integrating vectors be in that case? Again, they are given by the rows of A prime, but in that case, the first row of A prime would have a 1 at position 1 and be 0 elsewhere. The second row would have a 1 at position 2 and be 0 elsewhere, and so on, if A prime would be equal to the identity matrix. Now, what would that mean then? Well, remember, the co-integrating vectors contain the coefficients of our time series in the co-integration relations. So the first relation would only have y1, and so it would say that y1 is stationary. The second co-integrating vector would only have a coefficient 1 in front of y2, and it would say that y2 needs to be stationary, and so on. So in that case, we would have n co-integration relations. That would mean that all series individually should be stationary. But that can't be, since we started with a vector yt that is integrated of order 1. So in other words, you can only have n stationary linear combinations among n series if the original series were already stationary to start from. Otherwise, you can only have maximally n-1. Okay, so how do we use now this alternative formulation of A prime to arrive at our Phillips triangular representation? Well, let us denote the co-integration relations by Zt, and they are by definition equal to A prime times Yt. Now plug in our equivalent representation of A prime over here, and then you will see that you break up the n-dimensional series yt in a subvector denoted y1t of dimension h, and another subvector y2t of dimension n-h. We've then almost arrived at our Phillips triangular representation. For the first set of equations, you simply bring y1t to the other side. For the second equation, you write down a bold representation for the series in differences of the second subvector, so the difference of y2t. Now, let's take a step back and see how we can understand this representation. The second set of equations tells you that y2t has a stochastic trend. You indeed have a random walk type model equation for all elements in this subvector. The difference is here equal to a stationary time series, or in other words, y2t itself has a stochastic trend. The first set of equations then tells you that y1t inherits the stochastic trend from y2t, and both are additionally tied to each other through the stationary co-integration relations, the Zt. Now let's practice with our example how to write down Phillips triangular representation, which I've copied over here, our example. So first, let us try to obtain the first equation of Phillips triangular equation. The key ingredient there is the co-integration relation Zt, which is nothing more than A prime times Yt, and we have obtained A prime already in the previous video. That was just a vector 1 minus beta. Now in Phillips triangular representation, we have the series in levels that needs to pop up at the left-hand side. So simply bring this guy here to the other side, and we have our first equation. How to obtain the second equation? Well, that is very easy. In this case over here, the bold representation of y2t is already staring at us here on the slide over here. So I bring that over. And putting both equations then together gives you Phillips triangular representation. Again, the bottom part is generating the stochastic trend. You recognize the random walk model from last week. y1t inherits the stochastic trend from y2t and has additionally the stationary co-integration relation that ties both series together in the long run. All right, so we've seen Phillips triangular representation. Remember, it has on the left-hand side the series in levels for the first subvector and the series in differences for the second subvector of Yt. In the next video, we will compare it to yet another representation, namely the Stock and Watson common trend representation.